Polarity is a property of molecules that is a result of the uneven sharing of electrons, which causes electron clouds to become distorted. Ultimately, an ionic bond is essentially a turbo, extra polar bond. Nonpolar bonds, completely 100% nonpolar bonds, result as a function of two atoms of the same element bonding with one another, such as our diatomic molecules. And because they are the same atom, they will share their electrons equally, and that bond is said to be nonpolar. Polar bonds arise as a result of two different atoms with different electronegativities. For instance, hydrogen with a value of 2.1 and fluorine with a value of 4.0 give rise to the electrons being shared unevenly, and the bond is said to be polar. The more electronegative atom, fluorine in this case, will have a greater electron density and will be the end of the molecule that carries the negative charge. We symbolize polarity by two different methods typically. One way is to use the Greek alphabet delta, lowercase d. You're more used to capital D, in which we add signs to represent partially positive and partially negative, to distinguish from an ionic compound in which we have a full positive or full negative. Another way to represent polarity is with an arrow over top or overlaid on a bond, in which the point end of the arrow is the negative end and the feather end of the arrow is the plus end. Once again, the more electronegative atom will have greater electron density around it and carry the partial negative charge. Hence, oxygen with a higher electronegativity than carbon will be the negative end. Differences in electronegativity are actually a continuum that from completely nonpolar, in which atoms are the same and the electrons are very evenly distributed between the two nuclei. Essentially nonpolar, or what we would consider to be more or less nonpolar, could arise if, according to the electronegativity chart, such as for nitrogen and chlorine, in which the electronegativities are the same, given to one decimal place, and you will see differences in electronegativity from chart to chart. Or if the difference is small. For instance, carbon with an electronegativity of 2.5, hydrogen with a value of 2.1, often you'll find hydrogen with a value of 2.2, giving a difference of 0.4. If the difference in electronegativity between two atoms 0.4 or less, the bond is considered nonpolar. So in our chemistry courses, we want to consider the CH bond effectively a nonpolar bond, even though one could argue that it is ever so slightly polar towards the carbon being the negative end. We will consider the CH bond to be nonpolar. Then we have differences a little bit greater of about 0.8 between bromine and oxygen, in which the electron cloud is distorted towards the oxygen end. And we have more polar, such as between hydrogen and oxygen, in which the electron cloud will become even more distorted and the electrons will spend time closer to the oxygen. One could look at the hydrogen-halogen series, in which hydrogen is combined with fluorine, chlorine, bromine, and iodine, which you can see from the picture. The size increases down the chart, iodine being a bigger atom, and that affects the electronegativity. Iodine with a value of 2.5, fluorine with a value of 0.4. Electronegativity decreasing between these four hydrogen-halogen molecules. The polarity, therefore, decreases. Polarity is actually a measured property, and it is called a dipole moment, measured in dBs, named after somebody. And unlike electronegativity, which is a calculated number, polarity can be measured. So if we notice the difference in electronegativity is greater, the dipole moment, or polarity, is greater. If the difference in the electronegativity is smaller, the dipole moment is smaller, with hydrogen iodide being effectively nonpolar. The colors in these pictures are meant to show the gradation or the continuum in the polarity. So let's take a look at some molecules. The first and most important thing is that we need to start with a Lewis structure. So being able to draw effective Lewis structures for these molecules is important. Then we can decide on the polarity of the bonds. We can say right now, since oxygen is second only to fluorine, that these bonds are all going to be polar. Next, we need to think about the 3D shape of the molecule, and paying close attention to that 3D shape, then we can explain and determine the polarity of the molecule. Again, we want to distinguish between the polarity of the bonds and the polarity of the molecule. So having drawn a Lewis structure for these three molecules, we could use an arrow to represent that each of these bonds is polar towards the oxygen being the negative end of the bond, and thus pointing inward for the water molecule. Now let's be clear that these Lewis structures do not give a full indication of the actual shape. If we turn to the shape, we will realize that carbon dioxide is a linear molecule. And a linear molecule, the dipoles, another word for polar bond, is symmetrically opposed and will cancel out, resulting in a nonpolar molecule. As opposed to on sulfur dioxide, when the molecule is bent, the SO dipoles are not symmetrically opposed. Certainly there is symmetry in the molecule, but the dipoles themselves are not symmetrically opposed and will not cancel out, resulting in a polar molecule. The same is true for water, in which the molecule is bent, this time bent resulting from the tetrahedron, but again the OH dipoles are not symmetrically opposed. They will not cancel out and will result in a polar molecule. Sometimes a single arrow is placed over a simple molecule to show the direction of the polarity, the negative end being the oxygen in all three of these molecules, but it will be oriented in a slightly different way in the sulfur dioxide because the oxygen's on the outside, and this of course being nonpolar, so we wouldn't draw any overall polar arrow for the molecule. Let's take a look at the following three molecules, which again we would need to draw a Lewis structure. You can see that we'll end up with these three Lewis structures, and all of these bonds, with the exception of the carbon-hydrogen bonds, all of these other bonds are indeed polar. So let's draw some arrows pointing towards the nitrogen, which will be the more electronegative atom in ammonia molecule, and towards the oxygen in this formaldehyde molecule, and outward towards the fluorines in the CF molecule. In the case of ammonia, the one unshared pair within the Lewis structure, within the molecule, causes a trigonal pyramid geometry in which the NH dipoles will not be symmetrically opposed, will not cancel out, and resulting in a polar molecule. The same is true for the formaldehyde. The CO bond is not symmetrically opposed by any other equivalent polar bond within the trigonal planar geometry, and therefore will not cancel out, resulting in a polar molecule. Even though this end of the molecule is effectively nonpolar, we will end up with a dipole represented in this direction. On the other hand, fluorine, being very electronegative on the outside of this carbon tetrafluoride, these four dipoles are symmetrically opposed within the tetrahedral geometry and will cancel out, resulting in a nonpolar molecule. Of course, even if you did think of it as a cross structure, in this particular structure, you would result and probably say, great, cancel out, nonpolar molecule. So if we were to break out our pink arrow, we would say nonpolar. For this molecule, we could show polarity in this direction, and we would show polarity in this direction. Draw Lewis structures for these. Having drawn Lewis structures, we can see that one could draw a Lewis structure in which the fluorines were opposite in the Lewis structure, or we could draw a Lewis structure in which the fluorines appear to be side by side. In the case of only one fluorine, of course, the one fluorine could be placed in any of the positions. And it's time now to take a look at the actual shape of these molecules. It's tempting to think, if one were only to consider the cross structure, that the fluorine dipole carbon-fluorine bonds could cancel out. But it's important to remember that this molecule is a tetrahedron, and it's impossible to place the CF dipoles opposed, and so they are not symmetrically opposed. They will not cancel out, and this will result in a polar molecule. That becomes more obvious if one happened to put the fluorines side by side in the Lewis structure, but this certainly is a path to heading towards saying nonpolar when in fact the molecule absolutely is polar. With the single fluorine, it's fairly obvious that the dipole is not symmetrically opposed by anything opposite. The carbon H bonds are nonpolar, so the CF bond will result in a polar molecule. We could draw our polar arrows, and certainly we would represent them in this direction. Propane requires nothing special for us to look at because all of the bonds will be carbon-hydrogen or carbon-carbon bonds, and that will only result in a non-polar molecule. Certainly we'll end up with polarity when we have an oxygen bond in the molecule. Let's look at the Lewis structures. So in both of these Lewis structures, I drew the oxygen-hydrogen-oxygen-carbon bond bent, as it would be as a result of 4 domains, 2 unshared pairs. We will end up with a bent structure, and as a result, the carbon-oxygen and oxygen-hydrogen bonds are not symmetrically opposed and will not cancel out and will result in a polar molecule. Of course, this end of the molecule essentially nonpolar, but this end of the molecule absolutely polar. And if we were to draw our polarity arrow, we would certainly end up with this. Likewise, in this final molecule, we have a bent structure around the oxygen between the carbon-oxygen bonds, and the bent geometry, those carbon-oxygen polar bonds will not cancel out. They're not symmetrically opposed and will result in a polar molecule.